In this video, I want to talk about integration and some of the ideas that go into integration, especially some of the ideas that sort of get glossed over or that a lot of students miss from their math classes. These are ideas that end up being fundamental to using integration to solve physics problems. To get us started, I want to look at a somewhat trivial example, but one that will demonstrate the pattern that we'll often see show up when we apply integration in physics problems. Let's suppose I have a line and I want to know its length. Integration comes from the idea of addition. I take something and I add up lots of little bits to get the total. So if I took this line and I cut it into a little piece, I would need to know how long that piece was. I might look at it and say, well, this little piece has some differential length. Now, how long is that differential length? Well, it depends on my coordinate system. For example, if we put this line on the x-axis, I might say, well, that is dx long. And then I could take all these little dl's from all the little pieces, and I could add them up. And so if I were doing this in some discrete form, right, these would actually be a delta x, and I would add them up, and I would get my length, my total length. When we take some limit that delta x goes to 0, then this becomes the integral of dx between some limits. For example, I might integrate this from 0 to L, and if I do that, I will get back the length of my line. So we take our object, we chop it up into little pieces, and we're going to add up all those little pieces. That's the basis of integration. Now let's try a slightly less trivial example. What if I wanted to know the mass of this line? Well, if I wanted to know a mass, I can actually do the same thing. I would take this line and I would say, look, I'm going to cut up its little mass into some little bits. And I might say, well, this little bit has a mass dm. It might be the ith bit, so maybe it's dmi. Well, how much mass is in this little bit? Suppose I don't know the mass. Well, what else might I know? I might know the density. Now, if you remember density from, I don't know, third grade science or something like that, you always learned it was the mass of an object divided by its volume. And that is true when we're talking about density in everyday language. In truth, this would be known as a volume mass density. But what I've got here is a line. And so it doesn't have any volume. It's a one-dimensional object. It just has a length. In fact, I know its length because I just looked at it. Its length is dx. So I need something that when I multiply by dx, I get a little mass. So I don't want a volume mass density, which, by the way, we usually denote as rho. What else could I do? Well, if there's a volume mass density, maybe there is an area mass density. Although usually we don't call it area, we call it surface. This would be area, sorry, no. This would be mass per area, just like the volume mass density was mass per volume. But if I multiply this by dx, I'm not going to get back a mass. Instead, I'm going to get back a mass per length. So I need something that is mass divided by length, so that when I multiply it by, I need something that is mass per length, so that when I multiply it by my little delta length, I get back a little delta mass, a little differential mass, really. So I need what is known as a linear mass density, which we usually denote as lambda. That's the Greek letter lambda. And the surface mass density we usually denote as sigma. Now, if you took an earlier class, you might see the linear mass density sometimes is written as lambda. It might be written as mu in some cases. Again, it's just different ways of annotating the same thing. So if I know my linear mass density, I can get my mass now. Because my mass is now my linear mass density times my length. And then I do the same thing. If I integrate with respect to some limits, in this case it might be 0 to L, the length of my object, then I would get back my total mass of my object. So now let's use this to answer a real question. You may have learned in your first semester physics class about the moment of inertia, which sometimes is denoted as I. The moment of inertia, we know, is for a single point mass, is that point mass times its distance from some axis squared. But we don't have a point mass, we have a line. So let's see how we can use integration to find the moment of inertia about some axis. Let's choose an axis, for example, that runs through the end of this line of mass. If we do this, we need to, first of all, we need to chop it up into little mass bits. Each little mass bit has a little differential mass. How much mass is there? Well, it's going to be, I look at this and I need a density. This would be some lambda times dx, the length. That's my mass. How far is this little piece from my axis? Well, it is a distance x away from the axis. So now I can take what I know about a point mass and I can use it instead to talk about the moment of inertia of a continuous object. I just have to take all my little point masses and put them together. I'm going to take my little d differential mass times its distance from the axis squared, which is, of course, lambda dx times x squared, or in other words, this is lambda x squared dx. Now, we haven't even made a stipulation about what lambda is. Maybe lambda is continuous, and so maybe lambda is the total mass divided by the total length of this line. But it doesn't have to be. It could be anything we want. We haven't made any assumptions. Let's say that it is uniformly distributed mass. What does that give us? Well, now our little differential mass becomes the total mass divided by the total length times x squared dx. That's my little differential mass. All I need to do is integrate from my first mass at the beginning of my rod to my last bit of mass at the end of my rod. So I'm going to write an integral from 0 to L of my total mass divided by my length, x squared dx. Of course, the constant bits, the things that are constant with x, that's the total mass, that's not changing in x, and my length. And so I get the integral from 0 to L of x squared dx. And so when I work out the math, I get 1/3 the total mass divided by the length times the length cubed. And now I can cancel. And I get that the moment of inertia for a rod about its end is 1/3 the mass times the length squared, which if you look in a textbook, you would find that that is exactly the formula that you would get. So now you understand the basics of how we can apply integration in physical situations. Whatever we're interested in, be it the mass or the length, or if this were a second semester physics course, we might be interested in the charge. We can take our object and we can cut it up into some little differential bit that has a differential length or a differential mass or maybe a differential charge. And then all we have to do is add up all of our little differentials to get whatever it is, the quantity that we're interested in. This will often let us take some sort of discrete formula, such as the moment of inertia, and turn it into a continuous formula that will let us address the same situation, but now we don't have to worry about discrete bits. We can deal with continuous objects. And we'll use this over and over, whether it be to find area, to find force, to find field, to find mass, to find moment of inertia. There are lots of places where we can use this.